Hello, this begins our coverage of topics in Chapter 9, which introduces you to the concept of interrupts and also the use of hardware timers for periodic sampling of inputs. We'll first begin discussing the concepts of interrupts, and to motivate this discussion, we're going to talk about what we've been doing so far in terms of checking I/O switches. So far, we've been doing what's called polled input and output, in which we've been continually checking the I/O device to see if it was ready for data transfer. If your cell phone worked on this principle, then what would happen is that you would pull it out of your pocket and you would check it to see if somebody was on the other end of the line. Obviously, you can see two problems with this. Either you would check your cell phone too often, thus wasting time, or you would not check it often enough, thus missing calls. What we'd really like is for an I/O device to interrupt us when it is ready for data transfer, and that's exactly what your cell phone does. When your ringer goes off on your cell phone, you immediately stop what you're doing, you pick up your cell phone, and you answer the call. This is going to be more efficient because the processor or you can be doing other tasks while you're waiting for that data transfer, so it's efficient. So it turns out that interrupts are very important in modern processors in terms of handling I/O events. Let's first talk in general what an interrupt does on a microcontroller. And this is pretty much true for just about any microcontroller. We'll be executing a code sequence here, and then we will get an interrupt. What an interrupt does is forces the processor to deviate from its normal program operation and go execute some other code that's going to be called an interrupt service routine. It will execute this code, and then once it's finished executing, and that's called servicing the interrupt, it will pick up where it left off, where the interrupt occurred. So this interrupt looks like a subroutine call in that we're going and executing this code and coming back. The key difference is that you do not explicitly call this interrupt service routine. The CPU will call it as a result of the interrupt happening. It will be called automatically by the CPU. Your code will not call this. Let's talk about what happens when an interrupt occurs. Some information is going to be pushed automatically on the stack by the CPU. It's going to push the return address because we're going to need to know where to come back to once we finish servicing this interrupt. It's also going to push some information on the stack that indicates the current interrupt priority level. We're going to discover that interrupts have different priority levels, and this information that's pushed on the stack is going to save the current priority level. Then the CPU priority level is going to be set to the level of the current interrupt. This means that any other interrupts at the same priority level will not be able to interrupt this interrupt because we're going to need to execute this code and we don't want to be interrupted while doing so. Then the program counter is going to be set to what's called the interrupt vector, which simply means we're going to jump to this interrupt service routine. Once we're in the interrupt, what should we do? Well, the first thing we need to do is save the processor context. What this simply means is we need to save any registers that are used inside this code. Remember, this interrupt is going on behind this code's back. It doesn't know this interrupt is happening. And any registers we use here, we're going to need to save, because if we mess up the contents in these registers and we come back, then these registers will have changed during the execution of this code, and it's going to cause incorrect operation. So where we would save them, we simply push them on the stack. So any registers that you use while executing this code, you push them on the stack. Then we're going to service the interrupt. What that means is that we're going to take care of whatever event caused this interrupt to occur. Then we're going to restore our registers, and finally we're going to execute this special instruction RETFIE, which stands for return from interrupt, to get back to where where the interrupt occurred. And all this is going to do is simply going to pop the information that got pushed in the stack back onto the correct registers, which is going to end up jumping back to the instruction after the interrupt occurred. Let's note that if an interrupt occurs during instruction execution, the current instruction finishes before the interrupt is serviced. We're going to refer to our normal program flow as the foreground code. So this is typically in our programs is going to be the code we're executing in our main function. The code that's executed in the interrupt service routine, we'll refer to that as the background code. It's going on in the background. Recall that location 0 is reserved for the very first instruction that is executed, which simply is a go-to to the C startup code in our programs. After that is going to be some locations that are going to be called interrupt vectors. These locations are going to contain the address of the interrupt service routine for each possible interrupt source that the PIC24 supports. There are many interrupt sources on the PIC24 microcontroller. We're going to discuss some of them. We won't be able to cover all of them. Typically, they're grouped for hardware modules. For example, there are interrupts for the timer 1 hardware module. There are interrupts for the serial data UART hardware module. There are interrupts for the I2C module, and so forth. The address in the interrupt vector is given here. There's also a vector number that's associated with the interrupt. We'll refer to this occasionally. So this would be vector 1, vector 2, vector 3. More importantly, the PIC24 has a name associated with each interrupt server routine. These names are important because these are going to be the names of the interrupt server routines that we're going to write to handle these particular interrupts. So if you're wondering what the name is, for example, for the timer 2 interrupt server routine, you would look in this table and see that it's going to be underscore T2 interrupt. Interrupts have priorities. An interrupt can be assigned a priority from 0 to 7. Normal instruction execution has priority 0. An interrupt must have a higher priority than 0 to interrupt normal execution. And what that means is, in order for the interrupt service routine to be executed, it has to have a higher priority than 0. If you assign a priority of 0 to an interrupt, then it's disabling that interrupt. This would be equivalent to turning off the ringer on your phone. A call would come in, but if the ringer is disabled, you're never going to get that interrupt. An interrupt with a higher priority can interrupt a currently executing interrupt service routine with a lower priority. What this means in the cell phone analogy would be that if you're talking on the phone, you're servicing interrupt, and you're talking with a friend, and another call comes in and you recognize that it's from your parents or perhaps from your significant other, and you would say, hey, wait a minute, I need to take this call, and you would put the other person on hold. You would be servicing a higher priority interrupt. When a PIC24 finishes executing an instruction, it checks to see if there are any interrupts pending. If there are multiple interrupts pending, these are called simultaneous interrupts. What happens if there are multiple interrupts pending of the same priority level? Which one would get recognized? Where it turns out that the interrupt with the lower vector number, that is its first in the interrupt vector table, would get recognized. It says it's said to have a higher natural priority. Note that the vector number is this number in here, so it's whatever interrupt would come first in the vector table. As an example, if an int0 interrupt and an int1 interrupt occurred at the same time, then because int0 has vector number 8, which is lower than int1, which has vector number 28, it would get recognized before the int1 if they had the same priority level. Let's talk about the condition needed to enable an interrupt. And what we mean by that is that the ISR is executed when the interrupt occurs. Each interrupt source generally has a flag bit, priority bits, and enable bit. The flag bit is set whenever the interrupt condition occurs, which varies by the interrupt. The priority bit set the interrupt priority. The enable bit must be a 1, and the interrupt priority must be greater than 0 for the ISR to be executed, that is, for the interrupt to be enabled. Let's say that again. The enable bit must be a 1, and the interrupt priority must be greater than 0 for the ISR to be executed, that is, for the interrupt to be enabled. It's also very important to note that the interrupt does not have to be enabled for the flag bit to be set. The flag bit will be set whenever the interrupt condition occurs, regardless of whether or not the interrupt is actually enabled. Recall that we said that the PIC24 CPU, when it finishes executing an instruction, will check to see if there are any interrupts pending. How does it know if an interrupt is pending? Well, what it's doing is checking the flag bits of the interrupt sources. If any or if multiple flag bits are set or only one is set, it's going to pick whatever interrupt is enabled and is the highest priority with its flag bit set, and it's going to execute that ISR. So one of the things that you must be done when you execute the code in your ISR is that before you exit the ISR, you must clear the flag bit, or else when you exit the ISR, the PIC24 is going to go back, and before it actually executes the next instruction, is going to see, is there any more interrupts pending, and if this flag bit has not been cleared, it's going to think that this thing is still pending, so it's going to go and execute the ISR again, and the PIC24 will get stuck in an infinite loop continually executing that ISR. After reset, by default, all priority bits enabled bits are 0, so all interrupts are disabled. That means that no ISRs are enabled to be executed. So a trap is a special type of interrupt. It's non-maskable, which means it cannot be disabled, and it always has a higher priority than normal interrupts. There are two types of traps. One is a hard trap, which means that the CPU stops execution at the point at which the trap occurs. A couple of hard traps are oscillator failure. If it detects that the oscillator has failed for some reason, then that's a hard trap, has priority 14. And addressing error, that's also a hard trap, but that means that if you try to access, say, a word at an odd location, that's an addressing error. Soft traps, the CPU is going to continue executing instructions after the trap has been sampled and acknowledged. Two types of soft traps are a math error. This is an example of like a divide by 0, or a stack error in which the stack overflows and it becomes greater than the stack limit register. That's also a soft trap. Interrupt latency is how long it takes for an interrupt to occur to the first instructions to be executed in the ISR. In many applications, this amount of time is important. Here's what happens on the PIC24. During this instruction cycle, we get an interrupt. After we finish the instruction, we're going to note that the interrupt is enabled and has occurred. So the PIC24 is going to begin servicing this. By the way, this is going to be the instruction that's going to be returned to once we're finished servicing the interrupt. So this is the first clock cycle. We're then going to save the PC in a temporary buffer. We're going to push the low bits of the PC onto the stack. We're then going to push the status register, low byte, and also the 8 high bits of the PC onto the stack as well. And then we're going to execute the first instruction of an ISR. So the number of instruction cycles that it takes to get to this first ISR instruction is 1, 2, 3, 4. 4 instruction cycles. It's going to take 3 instruction cycles from whenever the return from interrupt is executed to pop this information off the stack and get back to the instruction that we're going to execute once the ISR has finished execution. So when an interrupt is recognized and ISR is executed, we can think of it as stealing time from our foreground code. So how much time is this? Well, we have the entry into the ISR, which is 4 instruction cycles. We have the amount of instruction cycles needed by the ISR, not including the return from interrupt. And then we have the exit from the ISR, which happens to be 3 machine cycles in the PIC24. We're going to look at the impact of this ISR overhead given a frequency of how often the interrupt service routine occurs in terms of how many times it's triggered per second. So let's take a look at this ISR overhead for some numbers. We're going to go ahead and choose an instruction frequency of 40 megahertz and an ISR body that's going to take 50 instruction cycles to execute. These figures here show the how often the interrupt occurs, every 10 milliseconds, every 1 milliseconds, every 100, and so forth. And you can see how the overhead for this ISR increases the more frequently it's executed. So here's some golden rules for when writing an interrupt service routine. The interrupt service routine should do its work as quickly as possible. Because when the ISR is executing, it is keeping other ISRs of equal priority and lower from executing, as well as stealing time from the main code. You never should have a software delay in an ISR if you can avoid it. This shows a screenshot of MPLAB program memory beginning at location 0. Remember, this location is reserved for the first instruction that's going to be executed after power up or processor reset, and an instruction is going to be placed here by the compiler that says go to _reset, which is going to be the entry point for the C runtime code. These other locations contain the special label _default interrupt. This is what the compiler places here if the user has not explicitly specified an ISR in their code for this particular interrupt. If this interrupt code is executed, then it means that the user did not expect this interrupt to occur, and it said that this interrupt is unhandled. What we have done in our library routine is we have written our own _default interrupt ISR that will print diagnostic information to the serial port, as this is an unexpected occurrence and you want to know if this occurs. If you did not write your own code for this, then the compiler is simply going to define this function as being a software reset. This shows our library implementation of the code for the default interrupt ISR. What it does is it copies the contents of the special function register intreg, which contains some information about the interrupt that caused this ISR to be executed. It copies that information into this persistent variable. Recall the persistent variable is not touched by the C runtime code, so that means it can carry information across processor resets. Then we're going to call this library function called report error, where we pass it a string, and report error is going to copy the string into another persistent variable, and then it's going to execute a software reset. The software reset is going to cause the processor to re-execute the C runtime call, and then go ahead and re-execute our main, which will eventually call the print reset cause library function. This print reset cause library function is going to detect that this persistent variable here is non-zero because we copied this information into it, and so it knows that the last reset there was an error trap. So then it's going to print some information out to the screen, parsing information from the special function register that's going to indicate some information about that last interrupt. The last thing we would do before leaving this print reset cause function is we're going to clear these persistent variables back to their null state. Let's take a look at an example, our first interrupt example. Here we have the sample project chap_test from chapter 9. And what this is going to do, it's going to test a divide by zero trap. Recall that a trap is a special form of interrupt that cannot be masked. As such, there is no interrupt priority to be set because it has a fixed priority, and there's no interrupt enable bit to be set either because it's always enabled. So this particular program is going to output a string that says hit a key to start divide by zero test. We're going to wait for a character to be entered from the keyboard, and then we're going to output a message string here, and then we're going to force a divide by zero here. Now what's going to happen is the divide by zero trap will occur since we have not defined our own ISR to handle this particular divide by zero trap. The default interrupt is going to be called, and we're going to see a message printed out to the screen that's printed out by our default interrupt handler. So here we have program I pick 24 trap test.c, and it's executing, and it's waiting for us to hit a key to start to force the divide by zero. So I'm going to go ahead and do that. I'm going to enter a 1 here and send that over to serial port. So that's caused the divide by zero. Now what occurs is that our default handler is going to save some, is going to be called because we had not written an explicit handler for this particular trap, and so the default handler is going to save some information in some persistent variables indicating that an unhandled interrupt occurred, and then it's going to execute a software reset. At that point, our code begins executing again. Our print reset cause function is going to detect that a software reset occurred. It's also going to detect that some information has been saved in some variables that indicate that an unhandled interrupt occurred, and it's going to print this information to the screen, which is going to be the priority of the unhandled interrupt and the vector number. How do we determine what interrupt occurred from this information? Well, we see this priority 11. That would indicate, since it's higher than 7, that would indicate that this is a trap. And going back to the slide, we see that a trap with priority 11 happens to be a math error. You can also identify the interrupt by this vector number. We can go look at that table. Let's go back and take a look at this table, and we see that vector number 4 is a math error trap. So if you ever see this message occur in your program, you can identify what the unhandled interrupt was from this information. At this point, we all our print reset function will print out the device ID and other information as before, as well as the oscillator choice, and then we're back executing our program. What if you wanted to write your own interrupt surge routine to handle this interrupt instead of relying on the default interrupt function that is supplied by our library? This example shows how to do it. To define your own ISR, you need to define a function that uses the special name associated with the ISR. In this case, the name happens to be underscore math error. You also need to use a macro that declares that this is an ISR. In this case, I'm using the underscore ISR fast macro. Inside the function is whatever code that you're going to use to handle the interrupt. One of the first things you should do is clear the flag associated with the interrupt. In this case, this flag is called underscore math error. I'm going to clear it to 0. The other thing you need to do is do anything required to handle the interrupt. In this particular case, for divide by 0 interrupt, what you do is you clear the special function register to 0. At that point, I'm going to exit, and at that point, the divide by 0 interrupt is handled. So here I programmed my PIC24 with this new code that's called trap_test_handle.c. So it's waiting for me to send a key to do divide by 0. So I'll do that. I do it, and look what happens. I don't get any of the information printed by the default interrupt. Instead, I just go back up to the top of the loop and print this again. So all that's happened is that here it did divide by 0. I input the character, it printed out this message here. I did divide by 0. It jumped up to here, did this, came back. Now I'm printing out this string, hit a key to start divide by 0 again. It's important to note that this ISR math error is not called anywhere in this code. It's divide by 0 trap interrupt that's causing this code to execute. If we go back and look at the bootloader here, I can keep sending that 1, and I simply keep handling the interrupt and printing out the key again. I can do that as many times as I want. Let's illustrate a very common error, which is to forget clearing the flag associated with the interrupt. Here I'm going to comment out this code where I'm clearing the flag. Now what's going to happen now is that when this ISR is executed, I'm going to execute this code here. I'm going to exit. The flag is still set, so the CPU is going to think that this interrupt is still pending, and it's going to get stuck in an infinite loop executing this ISR over and over again, and the CPU will become unresponsive. Let's see how this works in practice. So I've programmed this PIC24 with my modified version of this code that's not going to clear the flag in the ISR. So let's go ahead and trigger the divide by 0. So I send it the key, which I just did. Now this string gets printed out, which is this string here after I input the character. Then the divide by 0 is triggered here, and now the processor is stuck in this infinite loop of always executing this ISR. Notice that I do not go back to the top of the loop and print this key again anymore. Print that message out anymore. I simply get blank space here. If I'm going to go ahead and send try to send something, but it's unresponsive. So at that point, the only way to get this processor out of this loop is to assert mclear, which I'll do remotely via the bootloader. I've just asserted master clear. And now I have reset the PIC24. I'm back executing my code. We'll close out this lecture by noting that if you compile this program and then look in low program memory expecting to see the interrupt vectors, all you're going to see is no ops. The reason for that is because all of our projects actually use a special linker script that enables the hex file that's compiled to be compiled for download by our bootloader. If you want to see the normal interrupt vectors, we need to remove this and recompile the program, which we'll do now. And after it's recompiled, you'll see that we'll now see the normal reset vectors down here in low memory. Notice that all of these vectors are the default except for our math error function, which we've written explicitly in our code. Let's go ahead and take a look at that assembly code. We're going to go ahead and find that, and it's going to be here. So here's the actual assembly language for math error. This clear word of 336 is it's actually clearing the R count special function register, and then it's doing a return from interrupt. Note that if you've deleted this linker script here, that this hex file is no longer compatible with the bootloader and cannot be downloaded by it.